Determining the age of the universe is a tricky thing to do. As of now, the most commonly known estimate for the age of the universe is about 13.8 billion years. This age was calculated by determining the current expansion rate of the universe, often called Hubble's constant, and extrapolating all the way back to the Big Bang. For a while, this measurement was considered to be really solid. Any other ways of measuring the age of the universe found results within a reasonable margin of error from our 13.8 billion year estimate. That is, until 2019, when a paper by Rees et al. Measured an age closer to 12.7 billion years using a different method, with a standard error that did not overlap with that of our most recent Hubble constant determination. This discrepancy is often referred to as the Hubble tension and is the primary motivation for my research work. The tricky thing about determining the age of the universe is that we often need to know distances to far objects in order to calculate an estimation. Determining distance has historically been one of the most difficult problems in astronomy and, if done incorrectly, would yield an incorrect value for Hubble's constant. My work tries to calculate an age estimate in a way that does not rely on distance measurements. In particular, I use stellar evolution. We know a lot about the way stars evolve because humans have been observing the stars for as long as we've been around. This is also useful because star ages put a strict lower limit on the age of the universe. The universe can't possibly be younger than the stars that exist within it. I work with really old star clusters called globular clusters for this work. The stars in these clusters are expected to all be around the same age, because the stars in a given cluster are all formed at the same time. Though they are the same age, these stars will not all be in the same place in their evolution, because more massive stars evolve faster than less massive stars. Because of this, we can plot a whole cluster of stars on a color magnitude diagram and compare the shape of the cluster's distribution to the shapes of a stellar evolution models called isochrones. For each cluster we study, we conduct a Monte Carlo simulation, meaning we generate some 2,000 different models, varying parameters like age, composition, and nuclear reaction rates. By comparing our cluster to all of these models, we can calculate an estimated mean and standard deviation for the age of the cluster. This process has been successfully conducted before by Blarney School alum Aaron O'Malley back in 2017. However, the error in those calculations was too large to help us in the case of Hubble tension. With the recent second data release from the Gaia satellite, however, we now have more precise data at our disposal than we ever did before. Additionally, my work also implements a way of further reducing error by considering how many stars from a given cluster are at specific stages in their evolution. This is significant because stars begin to evolve much more quickly after they stop fusing hydrogen in their core. Our goal is that by determining the ages of these clusters with reduced error, we can establish a useful hard lower limit on the age of the universe to help us further study and understand the Hubble tension.